We've been talking about gradient-free optimization, and our next topic is also gradient-free, but a bit more specialized, and that's discrete optimization. So in this case, we have design variables which are no longer continuous, but can only take on certain discrete quantities. We have seen an example of this already. That was the binary form of the genetic algorithm. We saw that because of the way we did the encoding with zeros and ones, that was actually a natural fit for discrete variables. And so that is an option that can be used when discrete variables exist. There's a lot of different nomenclature that is sometimes used when referring to these, but broadly speaking, these variables will come in different categories like binary. Yeah, so you might have binary decision problems, and that means that this design variable could be, a 0 or a 1. And that would be used to represent features that either exist or don't, right? So for example, let's say we're designing a car, for some novel application, and we're trying to decide, should it have headlights or not, right? So that's going to be a 0 or a 1 decision. You can have integer variables. And it doesn't have to start at 0, and it could be any subset. But let's say for this car, we were also deciding how many wheels it was going to have. Maybe it should have 2 wheels, 3 wheels, 4 wheels, 8 wheels. But we can't have 3.6 wheels, right? So that's an example of an integer variable. And discrete, we often mean to represent different categories. So for example, maybe the material of the body is going to be made out of aluminum, or steel, or titanium, or other various alloys amongst those. This is an example of discrete. Now, all of these sometimes are just called integer because we can represent each of these as an integer, right? We could say aluminum is 1, steel is 2, titanium is 3, and then it's an integer. And of course, binary is integer just with only 2 choices. So sometimes you'll hear integer programming is one phrase that's used, or integer optimization, integer programming. Sometimes discrete optimization, that's what we're using. Sometimes you'll hear combinatorial. And these two sometimes have different subtle meanings. But in our case, we'll just call them all discrete optimizations. There's just a case now where we only have discrete options. Of course, we cannot use derivatives anymore. We're already used to that now with the gradient free, but we are even more restricted in what we can do. Now, of course, this occurs in many types of applications. Some of the more common ones are say operations research type of problems. We're doing scheduling, resource allocation, supply chain management, a lot of these type of applications where these discrete choices need to be made. Another name that's going to be used here is mixed. So often you'll hear about mixed integer programming, and that just means that some of the design variables are discrete and some are continuous. Unfortunately, solving discrete problems is generally really difficult. We would say that they're NP complete, which means we can verify that something is a solution, but there's no approach, so no general approach to efficiently find a solution. So we often have to use heuristics. And often as the problems get larger, it becomes much, much harder to solve discrete problems. On the face of it, they would seem like they're easier, right? Because we actually have fewer options. Instead of this continuous space that has an infinite number of options, we have narrowed it down to a smaller subset. But because of the combinatorial nature of the problem, it actually becomes really complicated. So let me just give you an example. This is a very classic problem. It's called the traveling salesman problem. And there are many variations, ways to state it, but the simple one is like this. Given a list of cities, what's the shortest possible route to visit each city once, exactly once, and return back to the starting city? So let's say this is my starting city. Question B, where should I go? Should I go here and then here and then, should I go here or here next? And then where do I go? There's a lot of different options that you could come up with, okay? And obviously some are going to be worse than others. Like it's pretty obvious that I shouldn't like do something like this. That's clearly not going to be very optimal. I'm jumping all over the place. But what's the best route? In principle, we could try every combination, right? I mean, that's the advantage, or the apparent advantage perhaps, of these discrete ones, is that there's only certain options. So we could try all of them. Unfortunately, that's just not feasible for any decent sized problem. So here's an example of, say, a path. You know, I don't know that this is the optimum, but it's a decent solution. So say, for example, we wanted to visit all the state capitals of the United States. So 50 states, there's 50 stops we're going to make. That means the number of combinations of just 50, right? That's not a huge number, is 49 factorial, which ends up being like 6 times 10 to the 62, 10 to the 62nd power, which is an absurdly large number that is hard to even comprehend. You know, you take all the computers in the world running for a long, long time, and we couldn't even come close to even doing the tiniest fraction of that number of combinations. That doesn't mean we can't come up with really good solutions to traveling salesmen. We can. There are good algorithms that could solve that same problem, you know, in seconds, minutes at most, right? Where you know, as the problem gets larger, it gets a bit harder, but we can solve these really quickly. It's not necessarily the global solution. We don't know that. We didn't try all the combinations. That's a heuristic, but these can be really good heuristics that give us good solutions. Sometimes, like I said, really good solutions. But this does point out that we generally can't use this brute force approach and just try all the combinations. So we resort to heuristics, and there are some classes of problems, we'll talk about some in the coming days, that we can take advantage of some structure of the problem. So some problems have certain structure, like they have a linear structure, as we'll see, or they have a Markov chain structure, which we'll talk about. But if they have that kind of structure, we can come up with good solutions, sometimes get the global optimum that way. But for general problems, general nonlinear problems where we don't know any structure, these can be really, really difficult. Because they're hard, they're often, let's say, these are techniques to avoid perhaps, or to, yeah, I'll just call it to avoid. So sometimes if we can, we may want to avoid the discrete nature of the problem. This is often useful, especially if I have many continuous variables and a few discrete ones. And the fact that there's a few discrete ones, I don't necessarily want that to dictate the overall nature of the problem. I have to give up and treat everything as just a mixed problem where you have to use a discrete type of optimization solution. So I may want to try to avoid this. And even if I have all discrete variables, sometimes it's still, especially like I said, if there's no structure, it's nonlinear, may be desirable to not do that. So an obvious technique perhaps is just to round. That doesn't work every time, in part because sometimes the analysis doesn't make sense with a continuous variable. Sometimes it does. So let's take our car example. It obviously doesn't make sense to have 3.8 tires, but let's say we were using, you know, the cost, and we could calculate maybe a weight and sort of a fractional cost of a fraction of a tire. And so maybe it would make sense still from the optimizations perspective. The analysis would still work if I gave it a continuous variable, like optimize the number of tires. And let's say it comes out at the end and it says, you should use 3.8 tires. Then I might say, okay, let's round that to 4. Okay, that's one technique. That usually works better if the numbers are large. It's especially bad if it's binary, right? Like your decision 0 or 1, and you get 0.4. Well, you round to 0. I mean, that's kind of a big decision to round on. But let's say I'm trying to decide how many of these widgets to make, and my number is 697.3, and I round to 697. Well, that's probably a really good solution still, right? Because I mean, it's a very small fractional change that I made. It also usually works better if there's many more continuous variables than discrete. So usually better if numbers are large and let's say many continuous few discrete. Those are rules of thumb, but it can work well in a variety of situations. Sometimes it doesn't work at all, right? Like it may be that putting in a continuous number doesn't even make sense in the analysis, and I don't know how to deal with it, but oftentimes that can work. An improvement on that, well, there are several. If I have, let's say, many continuous variables and discrete, a good technique to do is to do that optimization like we talked about, and then you round. And let's say now I round to those 4 tires. Well, now I'm going to fix my tires at 4. And rather than just keep those variables as they were, I'm going to repeat the optimization, but now let those continuous variables change again with those tires now fixed at 4. Because now, there was some coupling between them, right? They're going to change a little bit, not a ton, but it'll allow me to improve my design a little bit more, right? So I can get back some of what I lost in that rounding there. A related technique is what's called dynamic rounding. And so that would be a case where, let's say I had, let's say I had half a dozen discrete variables and a whole bunch of continuous variables. Rather than, so I could optimize them all continuous, right? But rather than round them all at once, maybe I pick a couple of them and I round them, I fix, and then I do everything else. And then I pick another couple of them and I fix those. And then the last one, and then I do one final at the end where I let all the continuous vary. So rather than doing rounding all at once, I kind of allow some of that information to propagate as I make those other decisions, right? I allow it to know that I actually chose 6 instead of 6.2 here, and 2 instead of 2.4, or whatever. Okay, so those are various variations of rounding. Another technique, which we just said doesn't really work, well, it doesn't for those big problems, but an exhaustive search can work. Can be a good technique when I have many continuous and few discrete variables, especially. So a lot like this one, but if my number of combinations aren't that large, I could try them all. So for example, let's say, again, we're designing that car and I'm trying to figure out how many seats to put in the car. Well, I know I'm not going to put 100 seats in the car, right? There's going to be like 2, 3, 4, 5, 6, 7, 8, maybe at most there's 10 options. So I could run all 10 of those optimizations, right? I run the optimization when there's 2 seats and everything about the car changes continuously. And then I do the one with 3 seats, 4 seats, and then I just compare those and I see which one is best. And that will give me the right answer, right? I mean, assuming the continuous got the best solution, that will give me the best overall solution. And now if I have a few discrete variables, again, I could try all of those combinations. Of course, like we just talked about, that doesn't scale, right? If I've got lots of variables, this is just not going to work. But if there's a few, and there are many problems, right, where we said it's dominated by continuous variables, there are a few key discrete ones. It can be a very effective technique to just enumerate all of those. So that's not rounding, right? We're not doing an approximation there. We'll actually get the correct answer, but we have to run multiple optimizations. Rounding does introduce that approximation, but it still can work really well. And that approximation often is really mitigated by the fact that we can do that last optimization in the end where we fix those rounded variables and do one last optimization. That often gets us to a really, really good solution. Another technique is to, boy, that's horrible writing. It's just to change the parameterization. So parameterization, that just means how we define the problem. Effectively, those are the design variables, right? So parameterization would be, let's say I wanted to model this pencil, and maybe a first one would be, okay, it's a straight line, and then there's a straight angle, right? I make this little triangle at the end, and then the straight line. So I have a few variables, right? Maybe like a length and an angle and so on. But I could also parameterize it maybe by a curve, right? Maybe there's like this smooth curve that occurs here. Or maybe I parameterize it instead of a diameter. I could use a radius. That doesn't really make a big difference, but there are many options of ways I could describe it. And those are my design variables, right? So if I change the way I describe the problem, it may suddenly become continuous. This often requires a fair amount of creativity and maybe some experience, but I'm just making up an example on the fly here. Let's say we were doing some city planning and we were trying to figure out where to put the airport. And let's make our city easy and say it's this rectangle. And we already had some sites selected, like it could go here, here's a good option, here, or maybe here. Obviously, if there's only a few combinations, we could just try them, but this is just to give you the idea. That could be a discrete problem, right? where do I put it? 1, 2, 3, 4. Those are the design variables. Choose option 1, 2, 3, or 4. But I could also just say, okay, here's the airport. Let's make it a continuous problem and change and let X and Y be the design variables. And now I may have to add constraints, right? Because I may have said, well, there were reasons why I chose those, because there's, a bunch of houses over here and there's like a mountain over here and, whatever. But I could do that, right? I could come up with a problem that incorporates those constraints, and maybe I put some separation constraints, like the airport can move freely, but it has to be within, a certain distance away from the city center or whatever. Those are all things we can do, and I can then perhaps create a problem that's continuous, and I can scale up and maybe solve much more efficiently. Okay, so sometimes these things don't work, right? I mean, maybe our problem just doesn't lend itself well to a continuous representation. Rounding is just not a good option, or there are just way too many combinations. So we got to press forward. We're only going to really talk, we'll be fairly brief today. We're going to talk about one method that's frankly not really even a method per se. It's more an idea, and that's called the greedy algorithm. I guess to say it's more of a concept, right? So this is one of the simplest approaches. That's why I'll talk about it first. And the idea really is this, that we are going to reduce our difficult problem into a set of smaller problems. And often those problems will be a single decision, one choice. We will then make that decision and repeat that process again and again. So basically, break down a hard problem, has lots of combinations, and we'll just break it down into a sequence of small decisions. And after we make each decision, we don't revisit it. We don't go back and try it again, because that would involve trying all the combinations. So to give an example of one we already did, here's the traveling salesman problem, and we started here. A greedy algorithm that we could construct, and it's called greedy because we're going to do what's, we're going to do the greedy thing, what's best for this immediate iteration. We're going to go to the closest city. Okay, so maybe this one is the closest, and the next closest is this one, and then maybe it's this one, and then this one, and then it looks like I'm just doing an eyeballing, but it looks like this is closest, and then this one. And then I don't know, maybe it's this one. You can see how this sounds good, and it probably would give a pretty good solution, but you'll notice that, and this was fortuitous because I didn't really try this beforehand, but it's kind of left this guy on an island. So we're going to get through at some point, we're going to have to jump back there, and it probably would have been better to hit that one, while we were over here, for example, instead of coming back later. It just wasn't the closest. But that is a very easy process to do. And we can make it, we can maybe improve upon that, but that's the idea. Notice again, like I said, this is not an algorithm we can write down. It's something, it's a concept. And the advantage of this is that they're not going to scale up to this unbounded complexity where we have to try so many combinations. They can scale up well because every decision is just made from this really simple problems. But the disadvantage, as we've seen, is that we're generally not going to find the global optimum or necessarily even an optimum. In fact, some cases, there's a paper that will show that sometimes you can actually find the worst possible solution, but most of the time, if you construct a decent algorithm, it'll find a good solution, and it'll find it quickly. So this can be a really useful approach. So let me illustrate. I guess worked out that I illustrated a case where it didn't give me the global optimum, but here's another way to visualize that. Here's a picture of what's called a weighted directed graph. It's a graph, meaning, we've got these nodes and these connections. There's a network. It's weighted because each of these has some weight associated with it. That's like our cost. And it's directed, meaning we go from left to right here. We can't go backwards. So this is used a lot, for example, like in supply chain problems, transportation. So, or maybe an example that you might think about is you want to fly, you want to fly somewhere else in the world. And these are airports, right? Or maybe airports that we need to go to. And you want to find the minimum cost to get somewhere. And you got to think about all these different transfers. And of course, if I go to this airport, I have different options than if I went to this airport, and the cost from going from this airport to this airport are different than from here to here. So it's a sort of this directed problem, right? Where, each decision I make then affects my future decisions, and each decision has a cost. Okay, so a greedy algorithm in this case is always just going to choose what's the cheapest option, right? So from starting here, I've got 2, 1, 5, so my cheapest is 1, right? And now I've got 4, and so on, right? So this is the greedy path. 1 was the cheapest here, 4 was the cheapest. Here I'm choosing between 4 and 5, so I choose 4. And this last one, that's all I've got. So my total cost to get from beginning to end was, see, was that 15, okay? And like I said, this is a fast approach, right? It's bounded in complexity because we know, like I said, this decision is always going to be the same kind of thing each time, and it can be effective. So 15, but it's not the best solution necessarily. In this case, it's not. So in this case, this is actually the global optimum, and I only know that because, well, actually, we'll see some techniques we can use to do that. But in this case, it's simple enough. We could have just tried them all, but we'll talk about some techniques to actually do this in a better way. Here, my cost is, let's see, this is 7, this one's only 1, so 8, 10. So 10 versus 15. But notice, to get this kind of solution, right, I have to know, what's coming up and think through the full path, because in this case, this 1 was great, right? But I had to go through this 5, which, at the time I would not have wanted to choose that. That doesn't seem very good. As I get to this step, it's actually more expensive than here, but because there's this cheap one, overall it was the best. So it's that coupling, the combination of these that we miss with a greedy algorithm. Greedy algorithm ignores all the coupling. We just make a decision, lock it in, and make another decision. Just to give you some more examples, strategy games are classic examples, like chess. To take it all the way down, like the greediest one would be, I'm just going to make the best move I can make if all I was going to make is one move, right? And I'm not really great at chess, but I know enough that that's not necessarily a good strategy, right? You want to think a few moves ahead at least, and people who are really great may think even more than that. But that's an option that could work, and maybe if you're playing someone who doesn't have a lot of experience, that can work really well. If I know what's the best possible move, if all I'm making is this one move, and then I do that again, okay, what's the best possible move? Greedy doesn't always have to be one step. Maybe it's harder, right? But it may be greedy if I could still be feasible if I was like, well, what if I was thinking 2 steps ahead? But so this is a classic thing in strategy where there's combinations, and games are of course a little bit harder because there's now this dynamic component where an opponent is now making decisions that changes things and so on. So there's a whole area of game theory dealing with that. But that's just an example of another place where greedy options or greedy solutions can work well, right? Maybe with some bounded set of, maybe not one decision, but multiple. I give an example of the book of grocery shopping. Like say you were going to the store, you have a fixed budget, and you want to say get, let's say the most nutrition for a certain amount of cost, however you define nutrition, right? We'll just put that into our black box thing that spits out the nutritional cost or nutrition per cost. So we could come up with all sorts of greedy methods. There's not one method, right? So it could be that I always pick the cheapest item next. It could be that I always pick the most nutritious item next. It could be that I always am going to pick the food that has the most nutrition per unit cost, or it could be that I'm always going to pick, I don't know, anyway, we could make up all sorts of things, right? Depending on what we thought would be a useful approach. And some are going to work better than others, but they're all greedy in the sense that we don't go back and revisit the decisions and think about the best combination of them. We just think about them one at a time. Okay, now that I'm here, what's the next one best move? Now that I'm here, what's the next one best move? Okay, so again, this is not an algorithm we can write down. It's the concept. You'd have to think about your problem and say, okay, what's a good approach? And like I said, these are useful. They can be very effective, because if we can come up with a good decision process that works well, then we can greatly reduce the complexity of the problem, right? Where we reduce it down to a linear thing, right? Where we just make a sequence of one decision or a small number of decisions. That means we can scale this up to, if you're thinking about this weighted graph, I can make a huge weighted graph, and maybe finding the global optimum be extremely difficult, especially if I was trying to do all the combinations. But doing the greedy thing, it's not any harder, right? really fast and easy. Okay, so next time we're going to talk about an actual formal algorithm. We'll talk about branch and bound methods. So we'll get into how that works, and we'll be discussing a few different algorithms over the coming days. All right, that's it for today.